In lesson 10.6, we're going to look at some more angle arc theorems. There will be 4 theorems. It will be required that you get these in your pink booklets. The theorems will be pretty straightforward in their application as well, and being able to deduce them. I think it's pretty clear. But here's a picture again, just to kind of bring to your remembrance angle arc. So the last couple days we've been looking at chord and how it is the half of the sum of the arcs that it intercepts, and so on and so forth. We've got some inscribed angles, tangent. We've got a tangent angle, so we'll be looking for those in the theorems today. Starting with theorem 89, if 2 inscribed or tangent chord angles intercept the same arc. Now there's a lot of vocabulary in this chapter. I hope you are up to date on your green booklets. Be reading those, or be recording in those, and be reviewing those. So 2 inscribed, let's start with that. What would 2 inscribed angles that have the same arc look like? Okay, can you picture what that would look like? Here it is. I've got a red inscribed angle, and I've got this blue inscribed angle. And notice that they share the same arc. Okay, that's what we're talking about. If 2 inscribed angles share the same arc, what do we notice about their angle measure? 30 degrees. These are both the same, 30 degrees. They are congruent. Let's adjust that. Okay, let's see if that works for this arc. Sure, these angles, these inscribed angles, are always congruent if they intercept the same arc. Simply our conclusion, so let's record that. Then they are congruent. I hope that you can see we've induced it by looking at some examples, but I think you could probably deduce it. I won't go through the deduction here, but you should be able to deduce it directly from the rule set forth yesterday, in that the angle measure is half of the arc. And since the arc is the same for both, it will be the same angle measure. Something I think clever to realize is that if I move my vertex, notice that my angles don't change because my arc's not changed. If I want to change that angle measure, I need to adjust the arc measure. Well, we said it doesn't only work for inscribed, but it also works for tangent chord. What is a tangent chord? Think about that for a moment, okay? Here's a tangent chord situation. All right. I've got a vertical angle that is intercepting this green arc, and I have a tangent chord that also intercepts the same arc. Well, what do we know about these angles? We can see then that these angles here, EFG, is congruent to FHG. You can see that there's 43.21 for the same reason, right? Because we know how this angle is measured, 1/2 the arc, and this one is 1/2 the arc, so clearly they must be the same measure. So that's theorem 89, very straightforward, and the proof for it is pretty brief. Okay. Theorem 90 is the next one. Okay, we're going to look at if 2 inscribed or tangent chord angles intercept congruent arcs. So now we're just, it's very similar to the last one, but now they are intercepting, these angles intercept congruent arcs. According to my drawing then, I would want this green arc to be congruent with that green arc, and it looks like I need to adjust it so that it is. If I pull this around 112, that's going to be about as close as I can get it to being congruent. But since they're the same circle and these measures are the same, those 2 arcs, they are congruent, well, what would I expect about my angle measures? You guessed it, they must be equal as well, because they're 1/2. This has got to be congruent to that arc there. Okay? So really theorem 90 and 91 kind of come out of the same rule. Again, feel free to review these at any time if I'm going too fast, but we'll keep proceeding. Theorem 91. Theorem 91. An angle inscribed in a semicircle. Okay, so here I have a semicircle. I've got a circle with a diameter. Okay, I've got a semicircle. I'm going to construct an angle inscribed in the semicircle. So let's construct that. Okay. As I drag this around, now this is inscribed in the semicircle all the time. What can I say about the angle that has been constructed? What can I say about that? Give you a couple of seconds to think about that. What does that angle measure? What is this? Again, go back to your rules from last night. What does this arc measure? Well, a semicircle always measures 180 degrees, so that must be 90 degrees. That must be a 90-degree angle. In fact, we get a right triangle every time we inscribe it within a semicircle. So we'll record that here. An angle inscribed in a semicircle is a right angle. Alright, so another way to construct a right triangle. We have studied right triangles thoroughly. We've looked at Pythagorean triples. We've learned sine, cosine, and tangent. Triangles are very important, so you can expect on these homework problems for right triangles to surface from a semicircle. So be looking for it. And when you've got a right triangle, then go to town on it, like you've learned already. Moving on to theorem 92. The sum of the measures of the tangent angle and its minor arc is what? Now, let's piece that apart. Again, the vocabulary. The sum, what does sum mean? That means plus, right? The sum of the measures of the tangent angle. Where's the tangent angle? Well, here's my tangent angle, right? Those two segments are tangent. So there's my tangent angle there. And its minor arc, the key word there is minor. So remember that the tangent breaks the circle in exactly two arcs, a small arc and a large arc. So I don't have that one highlighted, this one around here. Well, what's the minor one? The minor one would be this one. So what is the relationship between this angle and that minor arc? I'm going to show you inductively, because the theorem left us really nothing to discover. It said the sum, so I'm gonna measure that angle. There's the angle, and I'm going to measure this arc. Measure arc angle. And then it says to sum them, so I'm going to calculate, and I'm going to calculate the sum of these. Oh my, 108 degrees. That must have been lucky, right? Well, let's adjust it. Notice that sum is always 180 degrees. 180 degrees. As my arc gets large, my angle gets small, and as my angle gets small, as my angle gets large, it gets, as my angle gets small, my arc gets larger. So I still have a sum of 180 always. Well, why is this? Okay, why is this? Well, to think through the deduction here, there's an auxiliary, actually. two auxiliaries that make this very clear. What auxiliaries do you think those would be that we could insert into this picture and use? Some of you are saying radius, and you're absolutely right. That radius is a huge auxiliary in this chapter, and I'm gonna carefully draw the radius like this. Okay. What do we have with that radius? We know that this is a right angle. That's a right angle. I have created a quadrilateral here. This is a quadrilateral, and I know that the sum of the interior angles of a quad, sum of interior angles of a quad is 360. 360 degrees. So if these two angles sum to 180, what does this one and that one have to sum to? 180 as well. So this one plus this one has got to add to 180 degrees. And there we have it. If these sum to 180 degrees, then since this central angle is the same measure as this arc, right? Central angle is the same as that arc, then we must have a minor arc that sums with that angle to be 180 degrees. Okay, so I just kind of talked through. I didn't do a rigorous two-column proof or a paragraph proof, but we've at least talked through the deduction on this one. Okay, so those are our theorems. We're done. Those are 4 theorems for this section. We are going to want to use and apply. Example 1, a nice example to use is yet another way to construct a similar triangle. From this, we've constructed many similar triangles, and a kind of a clever way to construct a triangle would be use our first theorem. I'm going to construct 2 inscribed angles. Let's display this with a different color there. I'm going to name these triangles. Call that A, B, put a point here on intersection. A, B, C. We have similarity here. We have similarity between this triangle and this triangle here. Can you see why? Well, let's look at our theorems. We've identified here that we have a arc, and that arc is being shared by both inscribed angles. Let me give it a different color here. Go orange. Didn't show up very well. Not at all, in fact. There's my arc. You can see my arc. Well, since it intercepts the same arc, what do we know to be congruent? We know that these 2 angles here are congruent. And by vertical angles, we clearly know that these are congruent. And then by AA, we know that triangle ACB must be similar to triangle DCE. So we've learned a lot about similar triangles, and here they creep up in this section because of some of the tool set that we've learned, and that we have some congruent angles, and we can see now similar triangles. We can answer all kinds of questions about that again. Okay, finally, one last example. One last example, and we're done here. Here I mentioned look for right triangles. We've studied a lot of right triangles. So here I've got a semicircle that a triangle is inscribed in. Well, we know that that's a right triangle from the lesson today. It's got to be a right triangle. We are given that the radius is 5, so that means the diameter is 10. We're given that BC is 8. This is a what? Look for your Pythagorean triples. 6, 8, 10 triangle. It says find the measure of arc BC. Find the measure of this arc right here. Well, it would be nice to know this angle. If I knew that angle, then I can use my rules to find it. How do I find that angle measure? Using our sine, cosine, and tangent. So we'll call this angle theta. Alright? So we can use any of the functions. If I use sine, sine of theta is opposite over hypotenuse. That is 8 over 10. So how do I find theta? But I'm going to take the inverse sine of 8 over 10. And then pull out your calculator. And take the inverse sine of 8/10, and you get 53.13. Theta must equal 53.13 degrees, and if that is 53.13, then this, and it's half of that, we need to multiply that by 2. So the arc equals 2 times 53.13 degrees. Multiply that by 2, and we get 106.26 degrees. I should say approximately. Alright, so with that, you've seen a few examples, you've seen the 4 theorems. Again, go back and review everything necessary, and that will suffice for today's lesson. See you in class.